Thank you. Good morning, everyone. Thanks for joining me today. I'm happy to introduce such a topic today. The broader motivation comes from two parts in theoretical physics. The first one is how space-time emerging from itself from the microscopic quantum degree freedom. This concept indeed is already encoded in the ADS-CFT correspondence. However, we still lack the detailed understanding of the underlying mechanism. And today we will use the formula algebra to understand such a mechanism in the framework SYK model. Additionally, how do quantum chaos and entanglement contribute to this emergence? And unfortunately, SYK-JT gravity correspondence can provide a unique laboratory to let us explore these issues. And crucially, it also allows us to study the Buck-Matters backreaction in a controlled way, which can help us to move beyond the pure gravity, but also can also let us see the iterating the Buck-Matter terms. This is important because somehow SYK's Buck theory is non-local. In the sense, we cannot use the Witten diagram to study the ADS-CFT correspondence, so that we use the other way to study the Buck-Matters backreaction, but it can be local. So in a sense that we can still apply the ADS-CFT dictionary to the non-trivial Buck-Matter coupling system. And let us first review the JT gravity. JT gravity is a two-dimensional dilaton gravity theory, and the Buck term involves a dilaton field that enforces the constant negative curvature. Because we can integrate out the dilaton field, then we get the delta function, delta r minus 2 lambda, so that we can enforce the constant negative curvature is a reason. And the second term is a boundary term. This term ensures a well-defined variation principle or Dirichlet boundary condition. Due to the dilaton enforces constant negative curvature, so then we can get the ADS2 metric. And then when we go to the D goes to 0 or the boundary, then the dynamics will be reduced to the so-called Schwarzschild theory. It's like here. And our fundamental field is not the metric now, it becomes F. And this theory has a Riemann symmetry. It can be studied exactly for the partition function, and it's a one loop SYK. Yeah. Any questions so far?
Manifold do you start with? You say you have a boundary, so you like half space, and then you get this metric.
You say here?
Yeah.
Yeah. So yeah, we have a boundary, Dirichlet boundary condition.
So you start with some kind of half space.
A disk or half plane?
Yeah. You can just here you say what is here we just you say boundary manifold or Buck manifold, and then make sure what do you want to disk.
Well, you have a boundary term, so you have to have a manifold with boundary.
Yeah. Just consider the Dirichlet boundary condition. So the all fields finish on the boundary.
How about the manifold? Is it
disk? Yeah. Okay. So any other questions? Okay. If no, let's now review the boundary theory SYK model. Indeed, this model consists of n Majorana fermion fields, and which can be interaction randomly.
This F, so this is the theory in the bulk.
It's a degree free from bulk, but now it's because now it's reduced to a boundary. So all degrees free are the boundary now.
Yeah, but because phi b is the dilaton in the bulk, right?
Yes, right.
And this
It's a function from the metric field. Yeah.
Okay, it's not non-function.
No function. Yeah, it's a general. You can say it's general function because the measure is like a df of f dot. Yeah. It's a SL2 metric. And then this SYK model, indeed it has n Majorana fermions, and it can have it can be the random O2O Q body interaction. Here I demonstrate Hamiltonian for Q equal to 4 case 4 body interaction, and the myofermion satisfy the usual anti-commutation relation, and this random complex J follows the Gaussian distribution. So we also have the usual variance J square over n to 3. And the large n and the low temperature limit, this model defects emergent conformal symmetry. And its effectuation is a Swanson again. So it's a first striking example to show the connection to the jetty gravity. Moreover, the SYK model is mathematically chaotic in the sense that the spectral statistics matches the random matrix theory. Gaussian orthogonal ensemble, Gaussian unitary ensemble, or Gaussian simple ensemble, these 3 ensembles. Oh, depends on your symmetry, your SYK Hamiltonian symmetry. Yeah, but you can match each one, either one case, then it's a chaotic model. Yeah. So let me first say the conjecture for the random matrix theory. The main random matrix theory is a connection to quantum chaos. Indeed, it's given by this BGS conjecture in 1984. They give they use a numerical solution and show the example and propose this BGS conjecture. But the conjecture contains that if a system is a classical chaotic, then its eigenvalues are correlated according to the random matrix theory. And this conjecture was also proved a semi-classical limit by these 4 guys in 2004. It's a German group. Yeah. And so now is why the random matrix theory becomes most important we always use random matrix to know whether the system is chaotic or not chaotic. This is the main reason for the BGS conjecture. And we can use this distribution of the difference of the eigenvalues to show the difference to see the difference between the Gaussian orthogonal ensemble, Gaussian unitary ensemble, Gaussian simple ensemble from this plot. And if the system is integrable, then we speculate it follows a partial distribution here. It's a difference between the Hamiltonian eigenvalue. Yeah. Yeah, probability distribution. Yeah. So, and then you can see the unique plot for each distribution. So it's easy to see the difference or deviation. So this is a usual approach from the SYK models chaos. Okay, any other question? Okay, let me go to other motivation of quantum chaos, OTOC, because it's more easier to see how the quantum chaos is connection to the gravity theory or ADS gravity theory. Indeed, is given by the most intuitive observable OTOC, a square of the commutator W and the V. And here I use the bosonic operators or bosonic series case. So I use the commutator here. Of course, even for Fermionic series, you use anti-commutator. For example, in the SYK model, we use anti-commutator. And then this, and when we say the V is momentum, W operator is a provision operator, then we can see OTOC is similar to the square of partial Q over partial Q of V. So if this has the exponential behavior like that, the exponent can tell us how the system is sensitive to the initial conditions. And this exponent, lambda L, is called the Yapon exponent. And indeed, this behavior is only up to the early fast time scale. It's T star minus 1 over lambda L log H bar. And this time scale has a physical meaning for that this shows that the Bohr correspondence principle only remains fair up to this time scale. And indeed, Martesina, Schenker, Stanford in 2015 also show that this Yapon exponent has the upper bound bounded by 2 pi kbt over h bar. So, but indeed, this proof is not general. At least it should have some two physical conditions. First thing is that the most physical condition is that the system should be unitary. A second consideration is that it's only for simple operators. If you consider a non-simple operator, it can be violated. For example, give one example, it's better. What is simple operator? Let me first define it. H is a Hamiltonian. For such an operator, we can always see the Yapon, the exponent always will not violate its bound if it is in the unitary system. But if we consider such an operator, then we can see the violation of chaos bound. And the one person already showed the example, and we see the answer. I remember the answer should be 2 pi over beta. Let me see the author's name. I forgot. Yeah, for this also he gave us a he used such an ensemble this operator and show the violation for the chaos bound. It's a good example. Yeah. So in this sense, at least we need a simple operator in the unitary system for this physical condition for such a chaos bound.
Is it clear why there should be a temperature that's bound?
Oh, why we should have a temperature? You say what is the physical insight to that?
Like what other people find chaos
Yes, it should be, but I think that you want to say that if t goes to 0, then Yapon exponent goes to 0, is right. Yeah, but let me think. In the SYK models, I think I remember if I'm correct, its answer is a beta j and here, and I do not have a good insight here. Yeah, sorry. For me, maybe the most simple way just by a dimension. I know that they should have a temperature layer. Yeah, but maybe I can use other dimension layer. For example, J is another one. I say J means that SYK have the J observable, so maybe I can also replace here. Yeah, for other class bound. Yeah. So, however, in the 2015, Medicina, Schenker, and Stanford also gave other conjecture. The saturation of the chaos bound in the conformal theory, field theory, indeed it possibly implies the ADS Einstein gravity dual. The condition is fully due to the OC's Yapon exponent computation. Yeah. So, but somehow, so far, I think it still does not have a contour ensemble for this conjecture. Any other question? No, okay. Where's okay.
Tau or 1 or 2, there's an integral in tau? Up there, no, up there.
Oh, where's tau?
Yeah, so here, so this is tau.
Yeah, tau. So it's like the integration between these two operators. Yes, but you can assume that O1 and O2 are independent.
And tau runs.
Yeah. Minus infinity to infinity.
Okay, so it's on both sides of.
Yeah.
So they
so indeed they do the computation very simply. Just do the OTOC1.
This is why it's out of time order, because
Yeah, yeah.
you stick to the same ordering, so it's always O2.
Oh no, it's different.
It's always O2 first and then O1.
You can see OTOC just by the first the C of T's meaning. Here is just a different operator. Yeah, yeah. But however, I just said if you consider such an operator, you can see the violation. Indeed, it's very easy to do computation because you can assume that they are independent. Then it just means that you do the 2 copies OTOC operators computation, and then you do the integration.
You always need something which is out of time.
Oh yeah, of course. For each OTOC, you should always do a different out of time order. Yeah, that's right. Yeah, yeah. So I just give us such a sum to say why people can do the computation and see the violation. Yeah, because it's just 2 copies of OTOC, so it's easy to do computation. Yeah. Okay. Let me do the last review for the later way I will use von Neumann algebras. The von Neumann algebra indeed is a most general way to classify the bounded operator. And it's interesting after the Liu Hong and his PhD student and also the Witten, let's see how it can be applied to the string theory or some quantum information problem. So it has 3 kinds of algebra. First one is a type 1 algebra. Indeed, it will have the O bounded operator. And it corresponds to the SYK as a finite n. So because it describes because we can include the all bounded operator in such a system, so that we think that the gravity can be described from this type 1 algebra. It's a physical meaning. For second algebra is type 2. We will lose something, lose of a pure state. And it corresponds to a large n expansion to all orders. So in the physical, this means that the theory corresponds to the gravity coupled to the matter field. So it's a semi-classical theory. And it has and also we can distinguish 2 small class. The one is type 1, other one is type 2 infinity. It depends on whether you have the maximum limit state. It has, it does not have. And the third kind of algebra is called type 3. This is the most better algebra. At least Witten thinks so. Yeah, he thinks that we almost lose everything, lose of the pure state, density matrix, and trace operation. So now I want to give an example to interpret this such a mathematical statement.
These you are assuming relativistic. When you talk about algebra, principle you are not relativistic.
Non-realistic?
Relativistic.
You say it's not realistic to the physical systems, right?
Yeah.
Yeah. So later I will say later how to beyond a little. Yeah. Usually it's not realistic. Yes, it's true because we always consider here we only apply this mathematical theorem to the boundary operator. Of course, it's not physical. Is what do you want to say?
Not realistic, relativistic.
Relativistic.
Oh.
Yeah, relativistic.
Oh, okay.
Because your SYK is not balancing. At this model.
It's not this much, right? Yes, yes.
So
But you can still classify the boundary operator because
times 3 QFT is a relativistic QFT.
oh yeah, but you can always apply it to the classify the boundary operator case. It's always general.
So my question is, if you have a non-relativistic QFT,
Yeah.
is type 3?
Is it okay? Whether we have a type 3 case? Let me see. I know that some people show that it has a type 3 from the SYK model. Yes. But for me, just based on mathematical theorem, we can apply it because it's just general mathematical statements. What after you insert, then you can have, yeah. Yes. Of course, you can insert the relativity condition there. Of course, you can do, but it's not the most general volume algebra. Yeah. Okay. But let me say a little about the one example to first distinguish the meaning why we lose the pure state or why we lose the trace operation. It may be more confusing between mathematics for physics. I think the good example is from the space system. It's always good from the space system to see it. So example is a SYK, and do the tensor product. So here the first here's a A region, B region, and I have the K spin and the K spin here. And the beta you can think is inverse temperature. And here we define the trace operation of A, and defined by psi A slot. And now we can find that the F A1, A2 does not equal to the F A2, A1. If A1, A2 only acts on the region A spin, so that means maybe most precisely they say the A1A, A2A, A2A. But here only for if the beta does not equal to 0. So in this sense, the F is not the trace operation here. If the beta is not in 0. So in this sense, there is a type 3 algebra. But if the beta is 0, then F_A1, A2 can equal to F_A2, A1. It becomes a type 2-1 algebra. And then indeed, when the beta equal to 0, it go back to the maximally entangled state. Okay. For this sample, any question?
So you want F to be your trace operation? Or?
Yeah. F is a trace operation. Think about it's like a trace. Low O, and it's like a little. Yeah. So we define it as the trace operation. But if beta does not equal 0, you will see F_A1, A2 does not equal to F_A2, A1. Because for the mathematical people, they always want to define the trace operation trace AB equal trace BA. This is a little different from the physics people because we know that for physics people, we like to say that Px does not equal 0, so trace Ps does not equal trace Sp. It's some languages issue. Yeah. So mathematicians always assume that it's yeah. So it's a language issue. So it's why this was so I think it's a good example to say why we lose the trace operation. Okay. Any other questions? Okay. If not, let me say what is the meaning for a loss of a pure states.
Actually, they're not equal because of the cross terms that appear with beta.
Yeah, it's right. Yeah. If it have the equal coefficient, then you will see the equal. Yeah, it's right. So let me, okay. If no question, let me go to the say why we lose the pure. What is the meaning for the lose of a pure state? Indeed, if beta equal to 0, then it will be the maximum mistake case. And then for the quantum field theory, the A has infinite degree and the B goes to infinite degrees. But indeed, this state is non-normalizable. So indeed, we cannot include it in the Hilbert space. So mathematician will tell us that we cannot write this state in the Hilbert space. But for physics, we still sometimes write this state because we use a truncated way to define such a state. So there's also difference between the physicists and the mathematicians. So it's it's a meaning to say that why for normal algebras to say that we lose a pure state for such a case. So any other question? Okay, no, okay. Later we will apply the such structure to see how the SYK's internal entropy fall in what class of operator in the large N limit. And indeed, if we take a large N, sometimes we lose the Hilbert space. So here, indeed, for at least I am physics, I will use the physical observable to distinguish from Riemann algebras. For example, I will use the maximum limit state to distinguish the type 2 and the type 2 infinity. Of course, you can also use the verifiers to distinguish the type 2 from the type 3. The verifiers can tell us whether you have the trace operation. It's not my today's focus, but you can see if you are interested in this approach, you can see Johanna's paper. I forgot the title. Yeah, just remember by Johanna in German.
Okay.
Yeah, Johanna. Yeah. I'm not good person to pronounce his name, sorry. Yeah, he claimed that he can use a verifier to know whether you can define a trace or not have a trace. Yeah, it's a good idea. I did not check the detail, sorry. But she gave many talk in somewhere. Okay, so now as a system to be more practical, I want to introduce the fermions or the matter field in the bulk. And today I will only introduce the Dirac fermions backreaction. Of course, you can follow a similar approach to see how the scalar field to be introduced and to see how the dual SYK model modified by the backreaction in our construction. They are almost similar. We consider the fermion case just for convenience. 6, 7. So we can add dark fermions now. Indeed, we will try to do the most general. Here, it's a Dirac operator. It's a kinetic term. It's a mass term. And also the coupling to the curved background. And then we can, after we introduce the bulk fermions, then we can find that the boundary action gets modified by the fermionic bilinears. The fermionic bilinears with non-trivial scaling dimensions. So here we can ask these two questions. The first question is, now from the bulk gravity language, we see the boundary theory, boundary effectuation is modified. Then what does the backreaction modify the dual SYK model? And the same question is, what does it teach us holographic chaos and entanglement? Yeah. So indeed, SYK's boundary coupling will depend on the conformal dimension. And this conformal dimension also depends on the Dirac fermion mass. So we will separate the discussion because when we consider different conformal dimension, the boundary, the SYKs will have a different modification. Any other question? So let me just use a result first. Okay, we utilize a two-point correlator of the SYK model to show the derivation. Okay, here I use the four bodies case. So four bodies coupling the SYK minus 2-point function. So now let us recall it. We know that the boundary effectuations denominators has 2 deltas power. So we can derive how many pairs of fermion we need. So the first 2 delta over the 1/2, then we should have the 4 delta. 4 deltas pairs. So if the Dirac fermion S is 0, then it implies delta is 1/2. So this means that I need to have a 2 pair. So in this sense that I should have 2 minor fermion coupled to the 1 boundary Dirac fermion. I distinguish the notation between the boundary and the Backreaction Dirac fermions. So in this sense, I should have such a coupling. This also disorder parameter Gij, Psi, Psi j, chi plus convention conjugate. And of course, I still have the SYK as a 4-body notation. So in this sense, after I consider this a full Hamiltonian, I can reproduce the Bach's this boundary effective theory again. So it's a same as the conventional SYK story. I said I can derive the boundary effectuation from the jetty gravity, but I can also derive the same effectuation from the conventional SYK model. Here is same. I consider jetty gravity theory with a matter, and I can derive this boundary effectuation. And now I can also plus the Backreaction term and to derive the same boundary effectuation. So it's same story.
What is chi?
Oh, chi is a boundary Dirac fermion. The degree of freedom is given by the Backreaction Dirac fermion.
Your Hamiltonian is odd in fermion number?
What is other fermion number?
3 fermions?
Oh yeah. Here, so it does not have a particle Hall symmetry in this case. No, does not commute with the particle Hall operator. But however, it's just one example. Indeed, you can find other cases. If you turn on the fermion Dirac mass, you can see the other cases can commute with the particle Hall number. Yeah, but indeed, it's not a big issue if you take a large n. The reason is, I think the reason is that if you integrate out G, it becomes 6 fermion again. Yeah, because if you integrate out G, I have this G also has Gaussian distributions of each G gives you psi chi. So after integrate out G, you get the 6 fermions effectuation again. So at a large n, I expect it does not have an issue. Yeah, does not have at least does not have a big issue even if we do not commute with the particle Hall operator. Yeah.
Should I think of G as being Graf?
Oh, here is a bosonic. Okay, I said is a Hamiltonian is fermionic. Here G is a bosonic. No, yeah, still bosonic. Yeah, yeah. But somehow it still works because it's a quantum mechanism. Because you can always in a quantum mechanism you can always Jordan-Wigner transformation to rewrite this Hamiltonian to rewrite the fermion degree to the Pauli matrix. So it's still you can define this such a system. So it's no problem. Yeah. But however, it's just one example. You can also write other cases for the even Dirac fermion for even fermion for even number of fermions couplets case is also okay, but you need to turn on the Dirac fermions mass. Yeah. But somehow, if I have time to talk further, you will find that indeed it's not a big issue to affect any large n properties. Yeah. Any question? Okay, if no, let me say more. So indeed, this GIJ still follows Gaussian distribution. So our variance now has one new parameters, G squared of n. Then this G will play a role of the Backreaction, a Backreaction strength, a Backreaction parameter. So in the gravity side, I also have the gravitational Backreaction parameter lambda. And by the comparing effectuation between the Back and the boundary, we can find the lambda in this proportion to G squared over J squared. Yeah. And so, and also due to the comparison, we can also derive the dictionary now. And indeed, this dictionary will have is very helpful for us to compute the entangled entropy, but it's not the bipartition between the space part, but for the other more non-conventional part. Yeah. So the dictionary now is Back fermion fields will correspond to the boundary Dirac fermion. So it's X side and it's and the back of the Backreaction will correspond to the random couplings in SYK. The precise here I mean the lambda and the corresponds with G. And it will be useful for us to compute the entangled entropy. Also have a physical Back gravities interpretation. So first, let me first define how we bipartition the Hilbert space. We define our Hilbert space like the Hn, tensor product Hd. For Hn means Majorana fermion. Here is a Dirac fermion. So it's a SYK par and also it's a matter par. And we always partial trace over the matter par to obtain the entangled entropy.
Maybe it's not exactly, just make sure I understand. So you add these fermions in JT gravity and you want to find the boundary dual in the SYK, what this corresponds to. So my question was, so from the ball point of view, when you add these fermions, what are the observables that you already know how to compute that you try to match with? Because I thought that JT gravity gives you some universal piece of all correlators of matter particles, and those sort of like decouple, and you can treat them as sources, right, for the computation.
Yeah. So
I'm a little bit lost. Like now you're talking about the boundary theory, but like what are we like? What are the
Here I just
theorems for
use the partition function to say that. Yeah, partition function.
you mean partition function in the boundary or the
I mean, okay. You can say principal and also the boundary. I mean, at first I consider jetty gravity with the matter part, like a fermion part, and then I can derive the boundary effectuation. This is from the Back gravity story. And then from SYK story, I can also give the modification and or Backreaction part, and then also derive the same effective theory. So they match each other.
I see.
But of course, you match each other, you will know how to compute the correlation function in large N.
I see. Sorry, but you haven't said this yet, or you
Huh?
haven't told us the bulk.
Oh no, not totally bulk because in the on jetty gravity side, okay, still it's bulk. Yeah. And I know this. If I already know this answer from the effectuation, we should get this boundary effectuation. And then now I want to say what is a modification part. Here is a modification part. After I introduce this modification part, I can just use the large N limit to reach this boundary effectuation again. Yeah. And this will be I want to literally answer in the large N limit. Later I will say a reason because now I have two independent parameters N and G. It's a little different from conventional, but however, you can always go back to the conventional ADS-CFT because you can add the G proportional to the 1 of n something or function of n, then you can go back to conventional ADS-CFT. But I hope to see the Back gravity, the ADS-CFT correspondence always at a large N. This is one motivation for us because if you use a large N expansion like a 1 over n expansion and to see the ADS-CFT in the SYK model, you will find some issues because the Back gravity theory is not local. This paper you can see the David Gross, Rosenhaus, maybe in 2019. Yeah. They proved that if you up to the cubic order matter, it's local. But go beyond cubic order, the theory is not local. So in this sense, because from the Witten diagram, we know that it's almost equivalent to computing by Feynman diagrams technicals. So you should assume that the Back theory is local. Otherwise, usually may not be fair. Maybe fair, I don't know. At least it's not critical. If it's not local theory. So I hope that my Back theory is always local and to see how the Backreaction can go to the orders and see what happened. Yeah, this is one motivation. Yeah. Okay, it's okay. Okay. So here is now Hiwaka space. I said it's my own SYK part and the part of the Dirac matter part. And I always want to compute the integral entropy, at least for our paper's result. We want to partialize the Dirac matter part. To obtain the integral entropy, and here we always use the fixed initial state. It's an unoccupied state in the occupation number basis, and we use this initial state and also partialize matter part to compute the integral entropy. So indeed, after we do this by partition, it's very interesting to compute the different bipartition of the integral entropy. Now, if we take a large N, the SYK part is indeed correspond to the pure gravity part. And then for this HD part, it corresponds to the Dirac fermion, the Back Dirac fermion matters part. So if we partialize this matter and to obtain the integral entropy, this means that we can get the entanglement between the graviton and the matter. So it's not the spatial path of entanglement now. So it's different from the conventional computation. But so I think it's maybe the first time to see the entanglement between the matter and the graviton from this way. But of course, it should be large N because the effectuation is correspondence only at the large N. We can see. So let me see our result. Our result is
Sorry, like what I'm saying, entanglement entropy is usually like some log of some trace. You compute some reduced density matrix.
Yeah. So I partial.
I guess it's the row inside the trace over n. It's a row n, and what's the thing in the middle? Ln.
And log. You like log? Okay. Okay. I usually use ln. Okay. I usually use ln. Maybe some people like log. Yeah. So however, now let's say that our universal result for entangled entropy, because we always consider this initial state. Of course, you consider other product states also okay. You always see the universal result. Yeah, here's the time. And we will see that the entanglement entropy initially grows and saturates to the final value. But the most interesting is that at a large n, we find that the entanglement entropy reaches the maximum. Will reach the maximum of the Hilbert space dimension. In this sense, that we will find that the graviton and the graviton and the matter will be the maximum entangled at the large n limit. So I think this can tell us that the backreaction indeed drives resistance towards the maximum entangle, allowing the intuition that the matter and the geometry is inseparable in holographic sense. You want to ask a question?
Yeah. So
entangled entropy.
Against time.
At the time, yeah, because you can always use Hamiltonian to do the involution. Yes.
Unitary evolution of the time.
Yeah. Of course, I have Hamiltonian. You can use Jordan-Wegener transformation to translate the Fermion degree to Pauling. Yeah, sure, of course. And then you can use you can increase n, and you will see how it approaches the maximum entangle.
So this value, asymptotic value.
It's asymptotic value. Yeah, because we cannot use the infinite n in the numerical solution. But we will see the almost reach the. I don't know. It's just a numerical observation now.
What's evolving in time besides entanglement entropy? Is the state somehow evolving?
Because you can use the Hamiltonian, because once you have a wave function, then you can use the exponential minus h t to do a time evolution to get the other wave function. Then you can.
Aren't you just in the ground state, or what?
No. I just use this state to demonstrate the result in our paper. But you can use any product state to do. But even for the ground state, you can also get a similar result. Yeah, we also try that. Yeah.
If you're using an eigenstate of h, why should there be any evolution at all?
You want to say that if I directly use eigenstate. Okay, I understand. If you directly use eigenstate, but it's different because here it has a random number. I cannot, if I use the fixed state, it cannot be for the all configurations ground state. Yeah.
So is it some sort of quench where you're turning on g at time equals 0?
It's a little similar quench, but it's different. But here I just see is our Hamiltonian because I want to get the same effectuation. Yeah. Let's say here is a pure quantifier, and I use this part to generate the method coupling's effectuation part.
So you're using an eigenstate of SYK, and then you perturb by the.
Oh no. Here I just you can use any product state to do you can also use any initial state, but I fixed it. I do not want to list state varies from the random coupling constant.
So you're picking some arbitrary state.
Yeah. Not the eigenstate. Not eigenstate. Because it's hard. If you want to fix a state, it's hard. It's impossible to choose the eigenstate because different configuration of the G will give the different eigenstate. So if you want to fix state, then it's impossible.
You pick some random state, you trace out.
Yeah.
And then it's the entanglement result.
Yeah.
Okay.
Yeah, that's the result. Yeah. So in this sense, now we can see the maximum entangle between the graviton and the matter. This is our conclusion. Yeah, here for numerical result. And then, so it also means that our state. Yes. If n becomes larger, then it will give the. Here is maybe m log 2. If n goes to infinity. M log 2 is this saturation factor. Yeah, it's asymptotic. When n goes to infinity, they will asymptotic to m log 2. You say, okay, because I can always take the infinite n there. Because I only can take the final n to do the computation. So when n. Yeah. And then we do the fitting and see it. So I don't know. Yeah, but just by numerical observation and also extrapolation. Yeah, and then we can see that it's almost. I can take. I mean, I remember it should be 24, 26 or 30. I forgot, but it's already large enough. Indeed, you cannot see the difference if you just see the plot between this saturation value or the n-log2. Almost cannot see difference. We just do it's a derivation. You get the algorithm values, and you can use the Hamiltonian to do the time evolution, and the partial trace the time evolution state. Then you can compute the integral entropy.
We are not using free fermion calculation. Free fermion formula, special formula. You're not.
Oh no, because it's not the free fermion here. Yeah. So it's not so.
You should not go to very large.
Yeah. So it's not a free fermion. So it's integrating fermion. So yeah, if it's a free fermion, I can use the analytic formula to do a computation, sure. But here it's not free fermion. Yeah.
Yeah, that's why I'm asking which method you are using. You can use tensor network. You can use what?
Oh, the tensor network is also one way, but we cannot use. Just use exact dimension.
Exactly.
Exact dimension. Yeah. Any other question? Okay. So now we say, okay, so when n goes to because when the large n and we reach this saturation region, indeed our state can be it's well approximated by this such the maximum entangled state. And if the n equal to n is a number of Majorana fermion, and there is a number of the Dirac fermion in the matter part. So if we do so, then these two states will have a same fermionic field degree of freedom. So in this sense, that we'll go back to the example that we said in the von Neumann algebra. So it gives a type 2-1 algebra. So now we can find it. Our result can be can give us that if it's a final n, is as expected for any final system is type 1 algebra. And then we can take a large n and get a type 2-1 algebra. And since we partially trace this Dirac fermion to get this type 2 and to compute the entangled entropy, and then it also implies that this Graviton's algebra should correspond to type 2-1. And also use this internal dimension to see the transition from type 1 to type 2 algebra. So it starts the internal dimension provides the microscopic mechanism to explain why emergent spectra appear and why the information laws appear in the dual gravity. Yeah. So it gives us a mechanism to understand the information loss problem. So any other question? Okay, if not, let me go to the generation. And the first generation, we want to say how to introduce the interacting matter. So we have a two generation. The first generation is that we want to introduce the interacting Bach matter. And this approach cannot be seen from our current Hamiltonian our current SYK dual theory. The reason is that any high order couplings or any high order metal couplings disappear in the large N limit. So that we should modify this theory a little and to see how the higher order coupling appear in our theory at the large N limit. So our way is that we introduce other distribution. So we introduce this addition term to the probability distribution, but also we still keep the Gaussian distribution term. And this distribution can also be, we can also use a diagrammatic way to understand the distribution. For example, for the Gaussian distribution, I will say that it is correspond to this connected two-point diagram. So you can see the chi, I, and psi. And for this term, it will provide other connected four-point diagram. Of course, here I only can talk about large N. So psi, of course, it should be bigger. Yeah. And here is psi, chi. And so even though we introduce this term, we can see the quartic coupling constant persistent now. And this result of this distribution, or this non-Gaussian distribution, is not suppressed at the large N. So in this sense, this non-Gaussianity fundamentally affects the effective theory. So it's the first generation, and because you can always use this diagram to understand the bucket local effect, the effective theory. So indeed, this effective theory is local. If you want to, if you just introduce it, we only have the bucket metal coupling up to the quartic order. Of course, if you want to higher order, you should introduce a static or higher order disorder distributions. So, any questions for this first generation?
Sorry, why is this a generalization?
Okay, because it's go beyond the Gaussian. In the past, in the first, I only have a such a distribution. Oh no, it's our disorder parameters distribution. So SYK model always needs a disorder parameter always need to follow the one distribution, and usually we use the Gaussian. So yeah, so here I want because if we just have the Gaussian, then all higher order metal couplings is suppressed at large N. So now I want to persist a large N, but still can have the higher order metal coupling. The simplest way is that I do not modify the Hamiltonian, but I introduce addition a quartic disorder parameter distribution here. Then it will give us and then we can also use a diagram to understand the distribution's effective theory. For example, if I introduce data, it gives a connected two-point diagram. And then for this diagram, it gives us a connected four-point diagram. Of course, if we want to higher order more, you just introduce static or high order couplings. So it's a very diagrammatic way to understand the distribution. And you can also think about this does not have any issue about the simulation, because here it gives you can say it's a G, because you can always sum over the I1 and give a G K1 K2 star. Here it gives a G K1 K2. So again, it's a positive definite distribution. Yeah, and okay, I expect you can use a similar way to generate the positive definite distribution and to generate the infinite order disorder parameter. Yeah. Yeah. So it's one good way to understand it. And because now from this way, we can always use the large n and a small g perturbation to see how the bucket matrix appear, but it's always local. So in this sense, it's better than using the conventional SYK model to see the ADS deal because it's more simplified. Yeah, but we can see the all orders bucket matrix backreaction coupling. And also can do a simulation to understand it if we are lazy. Yeah. Any other question? If not, let me say a little. Let me say other generation is that we want to introduce the bucket Fermion mass. And in this sense, the bucket Fermion mass implies that the conformal dimension is not 1/2. So give one example is if I consider Dirac Fermion mass over square root minus lambda equal 1/4, it implies that conformal dimension is 3/4. So it will give us the iterations 3 minor fermion capital 1 boundary Dirac fermion. Rather than and it's not the Mercedes case, 2 Dirac fermion and 1. Yeah, this is for the Mercedes case. So it's an example we want to show that different conformal dimension will show different iteration or different iterations modification in the SYK model. Yeah. Any question from these two generations?
So the counting against I has to mention a quarter?
Yeah, here is 3, because it's 3 side, 1 Dirac fermion, so it's not cubic, now it's a quartic. Yeah, quartic again. So it's all iterations in the SY in the dual boundary theory. It is all depends on this conformal dimension. So different Dirac fermion mass will give a different conformal dimension.
So are you just trying to write down marginal couplings here, or some?
Yeah. Just write down the coupling. Just write down the coupling in the dual SYK model. After I introduce this dual SYK model, I can reproduce bucket theory as a boundary effective theory again in large n.
Sorry, the last line is.
Oh, here is for Mercedes case.
So psi has to mention a quarter and chi has to mention a half.
You say, what is conformal dimension for the psi? Oh, okay, I understand. For here, I just use I use this psi is just a 1/2. Yeah, for fermion is 1/2. For SYK part, so this psi is 1/2. Yeah. Yes. Chi should be. Let me see. Should be. I think. Indeed, I do not use this conformal dimension to show that. Yeah, it does not need to show because this chi just appears is just give this fermion bilinear. Only for this minor fermion will contribute this power. Yeah, you can think that I consider, for example, let me go back to this case. And if I integrate out this Gij, then we get the psi I, psi j, and 2 chi. And this will give the so I can get the same result for delta equal to 1. because it's 1/2, 1/2. And this 2 chi will give us the fermion bilinear. If I consider the mass this case, yes, it's like that. Yeah. Is that clear?
Entirely, but maybe you better go on. It's getting late.
Okay, okay. So now I just summarize our numerical solution now. So if we introduce this such a two generation, what the new result we get? First thing is non-Gaussian. For non-Gaussian case is that I extend our result will extend the saturation, time scale, and for the mass term, if I introduce a mass term there from mass this case to the massive case, then we shorten saturation time scale. This is our numerical observation from this result. So now we want to give the other conjecture, because if we consider quantum gravity, we should include the all high order matter coupling. And our conjecture is that if we include all orders matter coupling, it should correspond to the infinite order disorder parameter. And it implies that infinite saturation time scale. And it's a type 2 one. And the third thing, and indeed this statement is interesting because we know that intermediate time scale we do not have the maximum limit state. But we still can define the trace operation. So in this case, algebra is type 2 infinity. But we know that if based on some evidence, the type 2 infinity is correspond to the ADS black hole case. For type 2 one case, it corresponds to the de Sitter case. So in this sense, this algebra transition indeed is very interesting because it may have a measure insight on thinking about the transition between the ADS and the DS. Yeah. Any question? Okay, I still have 15 minutes. Yeah. Any question so far? So I have said, so I just, let me just summarize our quantum chaos result very briefly, because I only have 15 minutes. Here, we just want to say that the first, in our quantum chaos, we can also do the same thing from in the SYK, just use the symmetry to classify the random matrix theory. But somehow here is exciting because it's more exciting because now we have this disorder parameter, but the Hamiltonian has the same symmetry. So, but you know many observable, if I consider many observables expanding variables may be changed because we can, but because disorder parameter distribution is changing, then expanding variable is also maybe also changed. But somehow we find it's surprising. The first thing is that symmetry is not changing. A symmetry, sorry, not symmetry is not changing. Should be say our classification of random matrix is still the same. In this sense, that I use the TD defined by n over 2 plus n. N is a SYK's Majorana fermion number, and M is a number of Dirac fermion number. And our classification is the same as Polchinski and many authors black hole in the random matrix, this paper. Once you use the m is 0. Yeah. Okay. So we can just see the forecast. So if n over n is large enough, if n over n is large enough, we can find the symmetry still strong enough to classify random matrix theory, even if we not consider the Gaussian disorder parameters. But it's interesting because we know that if I change the disorder parameter in the SYK model, the effectuation is changed. So somehow we should feel surprising that the random matrix is still a good approximation to the spectrum. Yeah. Any other questions for such part?
We shouldn't find it surprising that what's
because we need to compute observer to know what the distribution we have. But this experimental value depends on disorder parameter. But the symmetry is not changed by Hamiltonian because Hamiltonian is not changed now. I just changed the disorder. But after I just change the disorder, but the symmetry is still strong enough, so we can strong enough to see the same classification of a random matrix theory as in the SYK. Yeah, everything are the same. It's not changed by the disorder. Yeah. That's one thing. Because Hamiltonian, if I use the Gaussian or not or with the non-Gaussian, they give the same classification. But the Hamiltonian is not changed. So this means the symmetry is very strong. But you know that the effectuation now is changed.
Did you flip m and n? So n is the number of...
n is SYK's Majorana Fermi's number. So it should over 2 becomes a Dirac Fermi's degree. Yeah. And then if m goes to 0, it go back to the SYK's result. But however, just a generalization. Yeah. Just generalization. Everything is same as random matrix and I think it's a random matrix and the quantum chaos Pojinski paper. They give us this table. Yeah. And I just get the same table. Even if I do a modification, even if I include the disorder, all things give the same table. So this means the symmetry is very strong. Yeah. But the effectuation, of course, is changing because I change the disorder. Yeah. So why? Yeah. So I just say it's a surprising numerical observation. So any other question? So let me give us a final quantum chaos conclusion here. Because here I just say the symmetry is strong enough, but what the observer can let us observe the difference between the Gaussian disorder or non-Gaussian disorder, or let us see how the high order coupling can give us a different result. So our answer is that this table or the classification random matrix theory just gives us a short range correlation because it can just be measured by some quantity called gap relation. But somehow we can also use a spectrum form factor. But spectrum form factor is like the 2 point is like it's like this. It is a partition function, and the spectrum function defined by see. Oh, okay, should be it's better. You can use this impedance or depends on how it is different disorders. Yeah. This is a low range correlation observer. After we compute this observer in the dual SYK model, we can find that the time scale will be changed by such a non-Gaussian disorder. So we propose that this long range correlation is better to help to probe the different higher order meta coupling. Yeah. Yes. Any question? So, even though let me give the outlook and the conclusion of and summarize our findings. So our findings that Dirac backreaction indeed gives us a maximum entanglement between the graviton and the Dirac matter. Of course, we consider Dirac backreaction because it's easy to do the simulation, to do a study, because at the final end, you can always see the final degrees for the lesser reason. But for the bosonic part, you can also do a similar thing. And I expect that you can also see the maximum entangle. The second finding is that we found an interesting thing is a type 1 algebras and a type 2 1 algebra transition. But also we can also see in the large n limit and with the infinite order disorder parameters case, we speculate that you can see that the intermediate time scale will give you type 2 infinity, and in the infinite time will give the type 2 1. So if some evidence is correct, it gives the ADS black hole, here gives a DS. So we can see the ADS black hole and the DS black hole, the transition from such a understanding. So, however, it should have a more thorough understanding to know whether this type 2 1 really correspond to the DS case. Is still possible. I think so. So we still try to understand something further. Third thing is that non-Gaussian and the Dirac fermion mass only changes the saturation time scale, but we always can see the equilibrium, but always have the equilibrium. Or we can say that always we can have the maximum entangle, even if we introduce this non-Gaussian disorder mass. Yeah, this result will not be changed. And for chaos, we can find that symmetry chaos still preserved. Will not be changed by disorder. But the long range correlation, like such as space-time form factor, we can see the time scale is changed. So we can use a space-time form factor or the long range correlation to probe the non-Gaussian disorder. And our outlook is that in the future, I think something can be understood further. The first thing is that whether we can really use analytical way to understand the high order couplings, and also if we have the what is non-perturbative effect to let us probe to understand the mechanism from for non-Riemann algebras. And because it's a SYK model is very close to the condensed matter system, so it's possible to use the lab to detect such the Backreaction effect. Okay, thank you for listening my talk. I'm happy to take any question. Oh, for the type 2 one, you can say it's a boundary size, but it's for Wheaton's paper, and they want to propose that if you see a type 2 one for Riemann algebra, it will correspond to the de Sitter, and for type 2 infinity will correspond to the ADS threshold. Yeah. So it's So for this size gravity.
But then the evidence you're seeing for that is just the change in the algebra?
Oh, no. I say the algebra change, just say that you can see if this proposal is correct, then you can say that the algebra is changing, then it implies the ADS DS transition. Yeah. If the proposal is correct, because I still not make sure that this proposal is correct, because for Riemann algebra just based on symmetry. It's a kinematic. Yeah, may depend on the dynamics, but if you believe Wheaton Honolulu's proposal, then the answer should be there. I do not have a follow comments. So now we try to convert this thing. It's still not fully concrete, but I want to say that another thing. If I consider SYK in the large n, but the late time, does this equivalent to the double scale SYK? Of course, a double scale limit. Yeah, so it's still U square of n goes to infinity like that, or it's finite. It depends on what you want to say. Such are they equivalent? Yeah, I think if true, possibly you can see this equivalence. Yeah. So in this sense, the large n, but the later limit will tell us the double scale limit. Then it may correspond. Then the may tell us this is a de Sitter. So in this sense, the lifetime so is a corresponding. It's one way to understand whether this ADS DS transition is correct or not. At least you can see some computations evidence. Maybe, yeah. I'm still not sure. And we can just compute the 2-point function to show that, yeah, by numerical way.
Thank you, Chente.
Yeah, thank you.